Lesson 6, we're going to talk about sketching functions from verbal descriptions. So the last lesson, we already had functions sketched for us, and we were kind of interpreting what their sketches were. This lesson, they're going to give us some information, and we're going to be sketching the functions ourselves. So if you look on page 195, Environmental Club is learning about oil consumption and energy conservation around the world. Jack says oil consumption in the United States has dropped a lot. Ashley says oil consumption in China is the biggest problem facing the world environment. Do you agree or disagree with Jack's statement? Construct an argument. And do you agree or disagree with Ashley's statement? Construct an argument. So from this, probably say that I would not agree with Jack's statement. If you look at the United States as the pink line on the graph, it's gone down slightly, but I would not say that's going down a lot. So I would disagree with that. And then for Ashley's statement, if we look at China, the graph for China, oil consumption here has gone up quite a bit. And they're actually passed us up, but maybe don't totally agree, making them sound like they're the only bad guys here about the environmental problems. So theirs has gone up a lot, but they do have a lot more people than the United States. So, you know, I think we could probably improve our situation here a little bit better as well. So look at example 1. We're going to talk about how these sketches of graphs can help describe its behavior. Scuba divers start to dive with a full tank of oxygen. While diving, she breathes at a constant rate. She checks the gauge after 22 minutes. What does a graph of the function look like? So you can see full tank of oxygen at 0 minutes. 22 minutes is about half full. So first thing they did, they said let's identify what our two variables are. That's going to decide how we're going to graph this thing. Time is one of the variables, and the other variable is the level of oxygen. We want to see the change in the oxygen level, so we're going to make that be on our y-axis so we can see the oxygen level go up or down, in this case just going down. The time almost always is going to be the x-axis. Time is going to do its own thing, and we're usually going to want to see the change in the other thing. So we analyze the relationship. We can see that the oxygen level is decreasing. It should be decreasing at a constant rate, we would suspect. And so they sketched a graph here. So they started out certain oxygen level, and it's going down, the oxygen level. So we draw this with a negative slope for our line to show it's decreasing. And hopefully at some point here, somewhere in here maybe, we'll resurface and get a different oxygen tank or something. Make sure, like they did on this graph, that you label the x-axis and the y-axis. Time in minutes, oxygen level, PSI, which is pounds per square inch. So to try it, the weight of the water exerts pressure on the diver. At a depth of 10 feet, water pressure is 19.1 pounds per square inch, or PSI. And depth of 14 feet, water pressure is 20.9 psi. Complete statements and then sketch the qualitative graph of this function. Qualitative graph, by the way, the book's not really getting into it here. Basically, a qualitative graph, maybe we talked about it before, it's just we're looking at, in general, what's happening. We're not necessarily using numbers here. So, for this, the input or x variable is going to be the water depth. A lot of times the first thing they give you is going to be your X variable. Again, we're probably more interested in what the water pressure is than how deep we are. Obviously they both go together, but you know, we don't want to get beyond a certain water pressure is kind of what we're looking at. So we'll make that be the Y variable, or the output is going to be the water pressure then. Okay, we make that our y-axis, then we can see how that water pressure is changing on our graph. So when we go to graph this then, technically, if we're just doing a qualitative graph, we technically would not have these numbers here, I would argue. But anyway, we're going to have our water depth underneath. So water depth. And make sure you put your units for that. That's water depth in feet. You can abbreviate feet if you'd like. And then we'll make sure on our y-axis we put water pressure. And you can abbreviate the pounds per square inch like we talked about as PSI. Okay, and so we can see what's happening. We were at 10 feet, it was 19.1 pounds per square inch. 14 feet is 20.9 PSI. So as we get to deeper water, what's happening with the water pressure? Is the water pressure increasing or decreasing? Increasing, yeah. 10 feet, 19.1, 14 feet, it increased a little bit there. So there is going to be some relationship here, a positive relationship. And again, we wouldn't necessarily have these numbers here on our graph. But in general, we could say that the water pressure is increasing as the water depth increases. Example 2, similar to what we did in the last lesson. Danica sketched the relationship between the altitude and time for one of her ski runs. Describe the behavior of the function in each interval based on her sketch. So the first one here, we're looking at altitude and time. So to start off with, you can see over time here, her altitude is increasing. So they're saying that she's on a chairlift going up to the top of the ski run. And then we have a constant section here. So she's waiting. She's staying at that same altitude waiting to go down. And then the last part there, it's decreasing. So that's when she's skiing down. And then she gets, you know, back to her altitude that she started at. Example 3, Jose is practicing javelin throws. What is the relationship between the height of the javelin and time, and what would the graph of this function look like? So this picture, none of the picture stuff is given to you. So we're just imagining, maybe. Imagining this is not here yet. Okay? So first of all, we'd have to identify our variables, which would be the time. Time, you'll notice, is the variable a lot of times. And then the height of the javelin. Height is going to be our y-axis. That's what we want to see the change in. And then we can analyze what's happening here. Whether you've seen javelin throw or not, you might have an idea what's going to happen. He's throwing the javelin, and then it's probably going to be increasing in height a little bit, hopefully. for him to get a maximum distance. He probably, doesn't want to just throw it straight or throw it downward. So it's going to increase in height, and then it's going to kind of max out, and then it's going to decrease in height until it hits the ground. So that's kind of what they sketched out here in their graph. You can see that's happening. And again, notice the labels here. We've got the height and the time labeled, so we can tell what's happening. This one they didn't put units because there wasn't any information really given in the problem. We could put seconds and feet if we wanted to, but this is just a general graph of what's happening regardless of the units. So if you look at the try it, Haru rides his bike from his home for 30 minutes at a fast pace. He stops to rest for 20 minutes. Then he continues in the same direction at a slower pace for 30 more minutes. Sketch a graph of the relationship of Haru's distance from home over time. Okay, and this is important when he's continuing, that he is continuing in the same direction here. All right, so we're looking at his distance from home. So he's starting out. Notice they've got this already set up for us here, which isn't always going to be the case. Time in minutes is our x-axis, distance in miles, and you might add from home. Okay, it's not working very good. It's not just how far he's gone, it's how far is he from home is what we're looking at. So you can see the first part here, he is riding at a fast pace. So he's starting out presumably at home. So he rides at a fast pace, so what's going to happen with our line?
Constant.
Okay, it is going to be constant, and is it going to be like a really shallow line or a steep line? He's going fast. A steep line. His distance is increasing very rapidly here. Does that make sense? Okay, and then he stops to rest. So if he stops to rest, this is the distance from home. Okay? If he's stopping to rest, what's going to be happening with his distance from home? Okay? So what should I do with my line here? Okay, it should be constant. I'm saying if I stop, I'm staying that same distance from home. Does that make sense? I'm not going back to home just because I stopped, but I'm staying at that constant, at that same distance. Okay, and then he's going the same direction, so he's still going away from home at a slower pace. So this one, how would this compare to our other one?
It wouldn't be as steep.
Okay, this one is not going to be as steep. It's still going to be increasing because he's still going the same direction away from home, but the line's not going to be quite as steep because he's going slower. It's going to take more time for him to get a certain distance if he goes slower. Does that make sense? Okay, so this is kind of a sketch of what's happening, what his distance from home would look like.